Hi guys, in today's video we're going to be continuing our look at the second derivative and what it can tell us about the shape and special points in a function. In the last video we paid particular attention to the way that the second derivative determines concavity of a function, how the function will curve. We also said how the second derivative provides information on maxima, minima and points of inflection, but we didn't take a look at those in detail. So let's look first at how the second derivative is connected to either a maximum or a minimum of a function. So on the left here we have a maximum of our function, the point where a function reaches a high value, at least locally. We know that elsewhere in the function it might actually go higher than that point, but within that small region it is the highest value of the function. What we know then is that before that point the slope must be up, and after that point the slope is down. And of course we saw last semester that at that maximum point the slope is 0. And so we can write that there, the first derivative of this function is equal to 0 at that point. For a minimum it's the opposite. The slope is initially down, after that point it's up, and at the minimum point, the slope is momentarily 0. When we take a look at what's actually happening to the slope there, in the case of a maximum going from positive through 0 to negative, the second derivative of the function will either be less than 0 or equal to 0. In the case of a minimum, we have a slope that goes from negative through 0 to positive. So the second derivative, in most cases, will be greater than 0. But it is also possible that at that point, the second derivative will be equal to 0. So if you know that you've got a point in a function that has a first derivative equal to 0, we know from last semester that that tells us that we've got a stationary point on our hands. And previously we've looked at how the slope of that function changes around the point. So we've looked for whether this function was increasing on the left and decreasing on the right of that point, which would tell us that we had a maximum. Or if it was decreasing then increasing around the point where it was 0, that would tell us it's a minimum. Now we have a way to work out the nature of a point without looking at the values around it. If the point has a first derivative equal to 0 and its second derivative is negative, it must be a maximum, because we can use that to tell us that the slope is changing from a positive to a negative value through that 0. In the same way, if we've got a point that has a first derivative 0 and a second derivative that's positive, then it must be a minimum, because a positive second derivative means that the slope of the function is going from a negative to a positive value through that 0. Next we'll take a look at points of inflection, and this is where we get to have a bit of fun. Take your pen or pencil and start drawing a curve, a spiral. At some point you want to stop and start curving the other way. Keep doing that. Do it over and over and over again. At some point stop and curve around the other way. In every one of those there comes a point where you stopped curving one way and started curving the other way. That's a point of inflection. Because what's happening with your curve is that you were curving one way, stopped and started curving the other. So in this first part, your second derivative was positive. In this second part, your second derivative is less than 0. So in the first part, the curve is curving up, it's like a bowl, and in the second part it's curving down, it's like a hill. Second derivative greater than 0, second derivative less than 0. Now, if the second derivative is a smooth function, if it's gone from a positive value to a negative value, that must mean that it passed through 0. All points of inflection, points where the function goes from having concavity up to concavity down or vice versa will have to pass through a point where the second derivative is 0, and that is our point of inflection. We've seen in the past that these points of inflection can occur horizontally, so we might have a function that comes down, levels off briefly, and then curves back down again. Again, our function was curving up, stopped, and curved down. Or the opposite, a function that is curving down, stops, and then starts curving up. So in the middle there is a point of inflection that can be horizontal, i.e. it would have a first derivative of 0 or be a stationary point. So we've just seen that all points of inflection will have a second derivative equal to 0. But that's not enough to identify them on its own, because as we saw on the previous slide, the second derivative can also equal 0 at a maximum or at a minimum. What we need to look for to determine whether a point is indeed a point of inflection is a change of concavity. On one side of the point, the function will be concave up, and on the other side it will be concave down. If we have that a function is concave up on both sides, then that would actually be a minimum. If it's concave down on both sides, that would actually be a maximum. So let's summarize what we know about the first and second derivatives at different points on our function. For a maximum, a minimum, or a horizontal point of inflection, the first derivative in any of those cases is 0, as they are all stationary points. Our point of inflection, though, can have any value for the first derivative. Our second derivative, though, for a maximum must be either less than 0 or 0 itself. For a minimum, the second derivative would either have to be greater than 0 or 0. For a horizontal point of inflection, and indeed for any point of inflection, the second derivative will always have to be 0. However, there's more to it than that. We know that at a point of inflection, the concavity must change. The sign of the second derivative has to go from negative to positive or vice versa. Together, this gives us enough information to identify any particular type of point on a function. If we look for points that have a first derivative of 0, then we find stationary points. The second derivative can then give us the information we need to identify those points. If the second derivative is less than 0, it must be a maximum. If the second derivative is greater than 0, it must be a minimum. If the second derivative is 0, that's not enough information to identify the point. We then need to look at the value of the second derivative around that point. If it's positive, then we know that we have a minimum. If it's negative on both sides, then we know we've got a maximum. If, however, it changes value from positive to negative or vice versa, then we know that we've got a point of inflection. And if we have a point of inflection, it just matters whether the first derivative is 0 or some other value. If it's 0, it's a horizontal point of inflection. If it's any other value, it's just a general point of inflection. We can use this information to extend our previous procedures for curve sketching. Now, instead of having to look at the value of a first derivative around a point to work out whether it is a maximum or minimum, we can simply go straight to the second derivative.